So I start off with acknowledgements to Rick Charles-Turnick for his usual improvisation and latest technology. Thank you, Rick. So I'm going to present on CO2 displacement processes in porous media. I feel a bit awkward doing this. There are chairs from Brazil, United States, Canada, Norway, Australia, and the UK. And of those countries, the UK is the only one without an active CO2 injection project going. We're trying to address that, but we are quite far behind. I also want to acknowledge Said, Hydra, and gang for their input to this presentation. So the motivation is that, as we know, many countries are targeting net zero emissions. Seems to be a magic date of 2050, which the UK has set. I understand that Canada has also, the Liberal Party in Canada has also set 2050 if they're re-elected as a time when they want to achieve net zero emissions. The Scottish Government, always keen to be one step ahead in the propaganda war, has made it 2045. We do have a distinct advantage in Scotland in that we have a large distilling industry which generates CO2 emissions, and so the strategy is just to drink the whisky a bit faster and we'll get to the 2045 targets sooner. Of course, net zero is problematic because, as Andrew was showing this morning, our energy consumption is going to increase, and the fraction coming from hydrocarbons is likely to increase over that period. And so we're going to have to find some way of dealing with not so much actually the energy, but perhaps the industry is going to be harder to decarbonize. And therefore CCS will be necessary if these targets are going to be met. There's no question about that. Deployment of CCS is slow. So a lot of that is for financial reasons. But what we can do is try and improve our understanding and perhaps look at using CO2 EOR as a mechanism for at least kick-starting CCS activity. I don't want to go into the debate about what the net impact of CO2 EOR is on CO2 emissions, but at least if it's a process by which we can get CO2 flowing along pipelines, it might help in the long run. So why is the research needed? Well, there are gaps in modelling CO2. A lot of advances being made. So we've heard presentations this morning in terms of how we describe multi-phase flow in porous media, and CO2 injection, especially at high pressures and low temperatures, can create problems with the CO2-rich phase becoming denser than the hydrocarbon liquid phase, and flipping taking place. So Russell John's work on that is absolutely essential. Diffusion of CO2 is another, in porous media, is another important thing. And how all of these geomechanical, geochemical interactions work together is very difficult, it's very problematic. Computationally, it's very intensive. A lot of work still needs to be done. And the workflows also need to be worked on. So that's the motivation. We need to develop understanding at all length scales, from pore scale to basin scale, and we need to have simulation tools that are appropriate for the length scales at which we're going to be applying or performing these calculations. And so we need appropriate modelling of if we're going to do CO2 EOR, or even if we're going to do CO2 injection into aquifers where there may be hydrocarbons present. We'll need to have an accurate description not only of the CO2 brine interactions, but also of the interactions with the hydrocarbon phase, as well as incorporating geochemical interactions, which are like geomechanical interactions, are often neglected in conventional recovery simulation work. Lots of uncertainties, and because of the problem with the fact that CO2 disposal is a cost, we have to do a proper cost-benefit analysis to actually get investment in these projects. So I'm going to talk, my talk is going to be based on work on two projects. The first is one based in the UK. It's probably the UK's most advanced, that's not saying very much, but it's the UK's most advanced CCS project at the moment. It's called ACORN, the objective being to reuse existing facilities and pipelines, repurpose these for CO2 injection, and just get a small amount of CO2 flowing offshore, and hopefully from a small acorn, a large tree will grow at some point. And the second is based on some work that a PhD student has been looking at in terms of the implications of CO2 WAG in the Brazilian pre-salt, and how to optimize that, and what is the impact of that on scale management, particularly calcite scale management in the production wells. So I'm going to talk first about the importance of using compositional simulation for CCS. It is possible to use black oil simulation for CO2 injection into brine systems alone by appropriate use of the PVT tables. But what we want to demonstrate is that in systems where there are hydrocarbons present, modeling of the hydrocarbon phase can have quite a big impact on our estimate of CO2 storage capacity and security. So the ACORN project is looking at starting off just by injecting 500,000 tons per year of CO2, basically taking existing pipelines that there are. If I can get Rick's clever tool to work. So so Aberdeen is just down the bottom here, and there's existing power station at Peterhead and pipelines which are CO2 compatible. So the Miller field is somewhere out here. I'm sure Mike will correct me if I've got that wrong. But this pipeline here was based on the Miller field, which has some CO2 content. So the pipeline is suitable for injecting CO2. So the idea is just to reverse the flow along that pipeline, which is currently mothballed, and have CO2 injection into the target site is this one here. So it's in the Captain Formation, and the site is now called the Acorn CO2 storage site. And the plan is to inject into that and have a backup store slightly further up. So if we reach capacity or there's some problem in this store, to be able to use the secondary store some distance away. However, there are 4 fields in the stored area, one of them which is still active oil reservoir. The other 3 are gas or gas condensate fields that have now been decommissioned, but still have remaining hydrocarbons in them. The calculations performed identified that between the 2 stores there'd be a storage capacity of some 92 million tons, which is ample for the project. Interestingly enough, the CO2 that would be trapped or stored would be trapped by various mechanisms. So you look at the bar chart along the bottom left, we can see that a fairly modest amount, only about 10%, would be stored by structural trapping against the cap rock and against the faults. The most significant component would be residual trapping as a irreducible CO2 saturation. About 20% would be dissolved in water. Actually, more would be dissolved in the oil, in the hydrocarbon, so mixing with the hydrocarbons, dissolved in the oil and in the gas fields. So CO2 is much more soluble in oil than it is in water. And so, although the volume of hydrocarbons is relatively small compared to the volume of water in these systems, quite a significant amount would be trapped in the oil. And some would still be migrating at a low rate after about 1,000 years. So the impact that the hydrocarbon fields have on this, well, there's an impact obviously due to the compressibility of the remaining hydrocarbons in these depleted fields. But in fact, the main thing that we were looking at was the impact of CO2 mixing with the hydrocarbons in the field. So the CO2 injection would take place down, planned injection would take place down towards the bottom. You can see there's a box here which identifies the store. This was the original store plan. It's actually been extended slightly up here now. But the injection would be down dip, and the CO2 would likely migrate into these depleted fields. The CO2 the mixture of the hydrocarbons and the CO2 would affect the plume properties, and that would then affect both the storage and capacity, as we're about to see. So the picture on the left shows the gas saturation after 1,000 years after injection. And you can see that for the plan, the gas will migrate up dip, but 1,000 years still remains within the previously defined store boundary up here. That's assuming no mixing with hydrocarbon gas. However, on the right-hand side, the calculations were performed assuming there would be mixing, and you can see that it only takes now 300 years for the gas to reach that same point. And in fact, if we take this forward, the right-hand picture forward to 1,000 years, you can see that the CO2 would migrate out of the store. So the mixing with the hydrocarbons is actually having quite a significant negative effect on the storage security for this system. Two reasons for that. One is that the mixture is less dense than the pure CO2, and so buoyancy-driven up-dip migration of the CO2 is stronger, and it will travel much further. And then the second reason is that the mixture, as it's propagating through the system, the CO2 is soluble in the water, but the hydrocarbon, the methane is not. And as a consequence, the CO2 is stripped out of this. So we're effectively displacing gas out of these disused or depleted gas fields. That gas is migrating, the CO2 content is dissolving in the water, but the methane remains as a free phase, and its density, the density of the mixture is reducing all the time as CO2 is being dissolved in the water. And so it's propagating much further. And so this is an important consideration in estimating the storage capacity. In fact, reduces the storage capacity by something like a quarter if the objective is to keep the displaced gas plume within the storage complex by the end of the defined time period. So the second thing I want to talk about is the importance of geochemical calculations in CCS or CCUS, should I say, perhaps here. So this is based on the Brazilian pre-salt. As we know, very familiar with this, high content of CO2 in the produced gas, produced fluids, and a desire in fact, not a desire, an actuality of re-injecting the CO2 as part of a WAG process. Obviously, we're constrained by various factors, a high degree of uncertainty in the reservoir description. I'd have a good understanding of the WAG process with CO2. And something I want to highlight is the impact on scale precipitation in the production wells. So obviously, we need a good hydrocarbon model. For this, we've used a standard Peng-Robinson equation of state. Peng-Robinson is not the best for CO2, but for multi-component hydrocarbon systems, it's a practical one to use. It's important to have the right number of components. So the figure on the bottom right is a simulated, what's the word I'm looking for calculating minimum miscibility pressure. In that calculation, it's identified that if you only use 4 components, as has been proposed, you can get complete stripping of the oil phase into the injected CO2 phase. And so you actually need to have more components, probably 6 or 7 at least, in order to be able to capture the impact of the heavier ends remaining in the oil phase and not being soluble in the injected CO2 phase. And so there will be some remaining oil saturation during the slim tube. That's the word I was looking for. There'll be some remaining oil in the system. We also need to capture the geochemistry accurately. So we have the speciation of CO2, and we have the mineral reactions that take place. The equilibrium constants are fairly well established for these types of conditions. A big gap in our knowledge is the rate at which these reactions will take place. Deep in the reservoir, that probably isn't particularly important, but in the near wellbore zones where residence times are short, then that lack of information on the kinetics and accurately modeling the kinetics given the changing temperature is a challenge. Also need to have an economic model to establish what will be the optimum design. So here's an NPV calculation, which is looking at positive contributions, obviously, from oil and natural gas exports, and then, I beg your pardon, and then costs associated with either venting or stripping and recycling the CO2, the gas separation process, and water disposal. And then on the injection side, there's a benefit from avoiding a carbon tax, but there's also costs associated with importing CO2 or natural gas, compressing it up and injecting it. And there's also a cost associated with the water injection, which in the pre-salt isn't insignificant. So a typical type of calculation might look at, on the y-axis here, NPV, which we've normalized to the waterflood NPV, and we can compare a pure gas flood, and on the x-axis we have the total amount of CO2 stored. So gas flood, pure CO2 injection will be the one that stores the maximum amount of CO2, because we're just continuously injecting CO2, but in fact the NPV is worse than for a water flood. And then we've used CMOS for looking at trying to identify the Pareto front with a range of optimal potential WAG designs. Comparing two WAG designs here, the base case that we started off with, which on the top here started with 3 years of water flooding, and then 6 months of water injection, 6 months of CO2 followed by 6 months of water injection. And on the bottom, we actually have the optimal design, which was divided into 3 stages. The first stage was a WAG stage with 4 months of water, then 8 months of CO2. And then during the period approaching breakthrough and shortly after, well, for a period after breakthrough, actually the period of the cyclicity increasing, so the period becoming much, much shorter, and then followed by longer periods in the towards the end. So that gives us the optimal design from that particular set of calculations. The question then is, what would be the impact of that design on the scale risk at the production wells? So what we've done is we've coupled a thermodynamic model that we've built at Heriot-Watt University. So a PhD student, Duarte Silva, has developed his own thermodynamic model, which he has coupled, or which has been coupled one directional coupling to the reservoir simulator, taking as output from the reservoir simulator the water flow rates and the water compositions in the production well over time, and then predicting from that the mass of scale that would form per day on the y-axis as a function of pore volume throughput on the x-axis. You can see that for pure CO2 injection, in fact, there's very little scale production. This system does not have an aquifer, so there's just a little bit of water production and some scaling taking place in the very early period due to compressional effects, but no significant amount of scale during the gas flood. During a water flood, we may get up to 80 tons of CO2, of calcium carbonate forming between from the perforations all the way to displacement to sea. So that's essentially a flash calculation to sea conditions. For the base case WAG, that was reduced to less than 50 tons per day at the maximum and a slight delay. And in fact, the optimal WAG design, because it also delayed water breakthrough, had a significant impact in terms of delaying the onset of scaling, and so would also be optimal from a scale perspective. So I just want to finish off by commenting that in order to model CO2 injection processes, we need to use appropriate tools for the purpose. and that will generally be compositional simulation, but we also need to use the tools appropriately. And so we have to have appropriate and sufficient components in both the hydrocarbon and the aqueous phases and the correct interactions. In saline aquifers, the CO2 may interact with stranded hydrocarbons, and so we have to include those in our calculations, and they may have a significant impact. Beneficial in terms of the CO2 will actually dissolve more readily in any remaining oil. However, if it mixes with gas, then the mix will become more mobile, and so the plume will migrate more quickly. And that will have a negative impact on storage capacity. Decision-making must take account of, we must optimize our NPV calculations, of course, to make this a viable proposition, but in that optimization process, we have to take account of the impact on other factors, such as the total amount of CO2 that would be stored, and flow assurances, such as scale prevention. And failure to model these processes appropriately may lead to incorrect estimates of storage capacity and net present value. So with that, I want to thank the sponsors of the research at Heriot-Watt University. I want to thank CMG for use of the software, and Energi Simulation also for their support. And again, I want to thank Rick for this wonderful little tool. Thank you.
Thank you, Dr. Mackay. Questions? Please stand to the mic. And while you're walking up there, I have another question. Excellent work in terms of looking at the sequestration aspect as well as the utilization aspect of CO2. You've looked at tapered WAC. Have you looked at tapered composition? Meaning initially you probably want a higher, more miscible kind of formulation and then taper off to a lesser amount of the richer solvent so that it will be a little bit more economic, enhancing the NPV?
No, we've not looked at tapered composition. We have started off with 100% CO2 composition and then realized that's not what's actually happening in the field. So we've looked at 90% CO2, 10% hydrocarbon, and what's more commonly used, which is 50% CO2, 50% hydrocarbon in the pre-salt. But we've not looked at varying that composition over time.
Okay, thank you.
Okay, very nice talk, thanks. In the beginning, when you looked at the impact of stripping out methane, why not just drill a recovery well up dip and pick it up? I mean, what were the volumes, and do you think it might be a silly idea, but
I can't say off the top of my head. Yes, it's interesting. We hadn't actually thought about that. We just threw our hands up in horror and thought that's horrible. We could look at the volumes. It might. My gut reaction is it may not be great. It may not be. You may end up producing a lot of water.
Well, I guess in return on investment also, if you have to wait 300 years, it may not be as great. But
yeah, I'll not be around then, so I can probably safely make a prediction at this point.
I was kind of, now, okay, you got to understand my background. So I'm an old fogey and done a lot of old CO2 modeling, right, over, for EOR. And I realized that your time scales and your temperature effects and your chemical stuff is definitely things, you need to calibrate them. And I think, but there's a large amount of uncertainty in your model. And I was just wondering, like you have EOR in the North Sea, like WAG type processes, and you also have them in Weyburn, and then you also have them in West Texas. And I realized that it's, the long-term effects, you have no calibration with those kind of things. But I guess what my opinion is that generally plumes or swept volume or whatever is strongly affected by heterogeneity. Do you think you would gain anything by modeling some of the short-term effects, within, human lifetime, let's say 30 years, to understand a little bit about plume migration? Because to me, when you're saying you're going to migrate into, with gas saturation and that kind of stuff, I think there's a lot to be learned from the short-term data that can help you understand the long-term data.
Sure, I think that's a really good point. In the Sleipner project in Norway, they've been taking regular 4D seismic, and so have tried to do that. And they found that their models predicted the plume disappearing off in a completely different direction from what it should. To correct it, they could do various things, including changing it, so they didn't have downhole temperature gauges. So I think a modest 1 or 2 degree change in temperature was sufficient to affect the density, and you could actually get the correct migration using the existing models, or even just by moving the top structure up or down a couple of meters was enough to set the CO2 going off in a completely different direction. So there's I think the point is there's a high degree of uncertainty with these, and therefore it is important to, during the active phase of these projects, to do as much of that calibration as possible. We have an advantage in that these systems are fairly well, for EOR, are fairly well described from years of hydrocarbon production, but there's still, if we're introducing a new fluid, there's still big uncertainties that arise from that. That's a good point.
Okay, thank you very much again.